So
No,
welcome everybody. Feel free to show your face if you'd like to. We can turn it off when the slides start. Maybe that's always a nice thing to do. My name's Simone Abram and I'm Director of the Durham Energy Institute, and I'm really pleased to be able to welcome you to this seminar. I think it might be the first one of the autumn, perhaps. And we're very pleased to have Cathy Hollis here with us today, who's Chair of Carbonate Geoscience at Manchester University. I did just say to her that you've all got a copy of her biography, and I'm not going to try and introduce that because it's beyond my level of expertise to go into any of the details. But it's very clear that she's had a very eminent career and has moved in and out of industry as well, which is very interesting, which means she has a lot to bring to us today. And she's going to be talking about a project which she was just telling me is coming towards its close. So I'm just going to hand over Cathy. Just to say that Cathy will talk for about 40 minutes. There should be plenty of time for chat and discussions at the end. And you're welcome to do that in person or pop questions into the chat as we go along. We'll be able to see that. So with no further ado, Cathy.
Okay, thanks very much, Simone, and hi everyone. Lots of familiar names and faces. So thank you for coming along. I was supposed to give this talk way back in March, and it got postponed, but I think for the better, because we've got some more data to show you. This is, as Simone said, we're coming to the close on my part of this project. It's a NERC-funded study that's joint with the University of Bristol and the British Geological Survey. And my part in this, I'm leading the whole thing. But at Manchester, we've been focusing on the characterisation of hypogene voids. So I'll just put this up and then share my screen, which will make this work better. Can you see that okay?
Yeah, that's good.
Good. Yeah, so it's characterisation genesis of hypogene void systems, which I will explain to everybody. Fiona Whitaker is leading the component at Bristol with Wenwen Wei, who's postdoc working on the project. They're modelling these processes. I'm not showing any of that today. That work is still ongoing. And then eventually with the BGS, particularly with Vanessa Banks and Andre Gonzalo Quiros, we'll be looking at the impact these voids might have on geothermal flow. And again, I have to come back another time and update you on that. So I'm really going to focus on the purely geological side of this and the characterisation work we've been doing. I'm going to start off by thinking about what hypogene karst is. It's something that is increasingly recognised by hydrogeologists in the modern and perhaps in the ancient. So I'll introduce that in a moment. I'm going to talk about whether it's present in the Carboniferous of the UK, or why it might be important, what its characteristics are, and at the last part, we'll be looking at some of the cements, the calcite mineralisation that we find within these cave systems. And I'm going to go into a bit of geochemistry at the end, so you might want to, take a bit of a breather at that point if that's not your thing. And then we can have a discussion really on what the impact might be on modern day flow. I think we're still, this is really where we're getting to it at the moment, working on this currently. I don't have any clear answers, but all your thoughts are very welcome. And on the right, I've got a picture of St Anne's Well in Buxton. As I'll go on to say in a minute, a lot of the processes that I'm going to talk about probably link into the modern hydrogeological system, which is feeding hot springs through on the Derbyshire Platform today. And I'm going to show you 2 or 3 examples of those springs. But this one in particular is very important locally in the Derbyshire area because it source for Buxton Water, and Nestle are bottling that just north of Buxton. But it's also used for the sort of for leisure facilities, and the Buxton Spa that has been refurbished in the last 10 years has water heated by it. So let's start by what hypogene karst is. When we think of karst, normally we think about processes that occur at or near the surface from rainwater, groundwater, that's percolating in from the surface and downwards, and results in dissolution of limestone because carbon dioxide is incorporated into the water from the atmosphere and from plant activity, and it can dissolve the limestone to form features that are very familiar to most people, things like limestone pavements, caves, and so on. And these processes operated in the past. So during the lower Carboniferous, the carbonate platforms that we see today in the Pennines have these sort of very irregular surfaces within them that I'm tracing out here, often with a thin soil clay material on top. And in the Derbyshire area, these are volcanic rich soils. There was a lot of volcanic activity at the same time as deposition. So these are continuities that will influence fracture distribution. They will perturb the flow laterally within the limestone. And then in the modern day, again, we see this very clearly in the Pennines today. We have quite big cave systems that have formed since the platforms were uplifted back to the surface. So these types of features were formed in the Carboniferous. These have been formed very recently, probably from glacial outwash meltwaters that were very cold and flushed through the system. And this is a phreatic tube. See a couple of cavers in here in Peak Cavern near Buxton and Calciton, and you get these big open systems that you can walk through or crawl through or whatever. But again, this is from water that's come in from the surface and down and flushed through. By comparison, hypogene karst is karst or solution of the limestone that has occurred from rising fluids that aren't directly genetically related to the land surface. So the water may originally have been meteoric, it may have been rainwater and groundwater coming to the surface, but it will have moved down very, very deeply and been very long-lived and eventually found its way back up again, usually along fracture systems. It's usually perceived to be fracture controlled. And we see caves that have these characteristics on the Derbyshire Platform. And one of the things we were, first things we set out to do in this project, as we'll see in a moment, is to identify whether these caves even existed or not. There was lots of features that suggested hypogene flow was taking place, but nobody had really tried to characterize it at all before. But when we go into some of the caves, and a lot of these are tourist caves, this is the Blue John Cavern near Calciton, very famous because of the Blue John fluorite. We see these vertical tube type systems that the arrows are marking, conveniently a staircase through the middle of it. And you can't really tell in here, but when you look at the side, the scallops that indicate that the water was flowing up and sort of circulating within these in a turbulent way as these caves are formed. This is another example not far away from there, where again you can see the ladder is going up, and we've got antiferrants at the top here. It's a vertical tube, but in this case it's lined by calcite cement. And so we identified 4 possible hypogene karst features within the Derbyshire Platform when we set out. These open systems, like we see here, this is also open, but some of that might have been mined out. Calcite cemented, this is definitely calcite cemented here. Mineralised, so that's calcite plus fluorite, barite and galena, and sediment filled. And the sediment filled I'm not going to really talk about. These had previously been a suggestion, these were hypogene by some previous workers. They're not that common, but they might well be hypogene. But I'm going to leave those today because they're a little bit more unique. And I'm going to focus on looking at these first 3 in here. So why might hypogene karst be important? Well, as most of you know, being involved in energy and geothermal, the Carboniferous limestone has been proposed by the British Geological Survey as a major potential low enthalpy geothermal resource in the UK. And this is a map from Jones et al. 23 BGS publication, which mapped out the distribution of the lower Carboniferous limestone, the Visayan limestone in the UK, and where it sits at depth beneath some of our major conurbations. You can see Manchester here, sort of quite red potential heat resource here, and in the East Midlands, some uncertainty in other areas because there is seismic data and it is really quite poor on shore. But this heat map indicates that there's potential to produce water and heat from these deeply buried limestones, potentially fluid temperatures up to sort of 80 degrees centigrade or so. So we're thinking about depths of several kilometres, 3-4 kilometres beneath some of our major conurbations. And we know that hot water can rise through the system, because another example of a spring, we have the Matlock Bath Spa, for example. This is coming out today at somewhere between 19 and 20 degrees centigrade. And this swimming pool is basically filled and heated by that water. There's no heat pump or anything. You can just go in and swim in it. A bit chilly, but it's a very pleasant 20 degrees. And of course, these are some of the very simple, easy uses of heat that we could look at. We mentioned spas, Buxton Spa, swimming pools, but potentially also far more commercial heat supply to homes or to industrial buildings or whatever. And in the Netherlands, the production of heat from the Carboniferous limestone for greenhouses and so forth. So lots of potential uses. And the question is, if we have hypogene karst in this limestone, is it going to help flow or is it going to perturb flow? And at the moment, I don't have an answer for that, but we can discuss it because you might have some views. So a little bit of tectonic stratigraphy. Most of you are aware, the Carboniferous limestone was deposited on the footwalls of normal faults, or at least faults with a normal, an extensional element during back-arctic extension in the Mississippian. So all of the blue areas here are Carboniferous limestone areas, areas of deposition in the Carboniferous. There were some areas of highland through the centre of Britain and up through the uplands, and then between these carbonate platforms were deeper water basins that accumulated reworked carbonates and mud rocks. The whole basin subsided and then was inverted again in the Pennsylvanian to Permian, and through reactivation of these major faults through here. And so most of the deposition took place Triasian to Visaean, and then was buried under this pile of sandstones and mud rocks until the whole thing was brought back up to the surface somewhere around the Pennsylvanian to Permian, Upper Carboniferous Permian. And I mention this now and I'll come back to it later. The interpretation of much of the mineralisation that I'm going to show you on the platform, the lead, the galena, sphalerite, galena, barite, fluorite, took place during that basin inversion at the end of the Carboniferous from fluids that were stored within these inter-platform basins being flushed up onto the platforms at that time. Now, there are other interpretations, but that's our working model at the moment. The hypotheses we were testing at the start of this project were that all these non-strata bound caverns that we saw formed at the same time from the same fluids, and that they were hypogenic, so that they were all formed from rising fluid flow. And we also wanted to see if the really coarsely crystalline calcite cements that we found within some of them were associated with that dissolution, with that upward rising flow. And if they were, what do those cements tell us about the conditions under which dissolution took place? And these were the mechanisms where we thought we might form hypogene caves, either from cooling upward brines. Calcite dissolves more readily at cooler temperatures. Injection of carbon dioxide or even H2S during igneous intrusion. This was an active period of volcanic activity, or fluid mixing, or some combination of the both. And I'll come back to that at the end. So what we spent most of the last couple of years doing, and particularly my postdoc, Alessandro Mangione, who's been working on this with me, is going, with the help of the Derbyshire Caving Club and John Gunn at the University of Birmingham, just going around as many caves as we can get access to without doing anything too crazy and dangerous, and just looking for evidence for hypogene karst. And these are the sites that we visited. They're all either tourist caverns or, in this case, this is Matton Cavern. It's a disused tourist cavern. Victorians used to go down there. It's closed down now, but it's quite easy access. Or mines, and disused mines that are safe to access. And you can see we've been across the platform. There's a bit missing in the middle, but that's because most of the sites in the centre of the platform are really hard to access, and often flooded, so not that easy to get into or safe to get into. It doesn't mean that they're not there. There are some reports that hypogenic features have been found. And you can see that many of these features sit along mapped faults. Down in the south here, there's probably some faults that haven't been mapped particularly well, but it's also close to the margin of the platform. And also that around Buxton and Matlock, there's an association with these hot springs. And this is one of these springs here with tufa deposits in it coming out at around 19 degrees. In this particular case, we've got this big hypogene cave here that's forming in the dolomite. So the green areas here are dolomitized. We have these caves forming in limestone and in dolomite. The other thing that's not on this map is that there was a center of volcanic activity down here to the south during the Carboniferous, and also around Bakewell and up towards between Buxton and here. So there was a lot of extrusive and intrusive volcanism during the Carboniferous. I'll run through the types of caves that we see. The first are these karst rifts. These are the biggest features. They're more 3 to 5 meters wide and often greater than 50 meters high. Really hard to photograph. This is Treat Cliff Cavern. It's a very famous tourist cave, and you can see that it goes up vertically. We're looking up at the ceiling, and we have closed, what's called a closed coupler at the top, which is essentially where the fluids have got stuck, and they've sort of, you have turbulent flow, and they've sort of started to swirl, and then they eventually find their way out, and it's almost like a meandering channel system through the roof. This is a similar cave system in Peak Cavern, which is very close by. Here, there's a hole up in the roof up here, and it carries on through that area. So these are sort of tube-like but connected in a vertical way through the roof system. And they can be associated with a much more complex set of smaller pipes and shafts. And you can see there's a bit of dissolution on the edges here in a horizontal direction, and starting to get some corrosion there. And we see similar features along faults. So this is Dirtlow Rake. It's a large excavated fault on the northern part of the Derbyshire Platform, east-west striking strike-slip fault. All the fluorite and barite and galena has been pretty much mined out of there, but there's still calcite along the walls. And then we see these chimneys rising toward within there. So this suggests that fluids that were moving along the fault were rising and circulating and creating these dissolution features, these rising chimneys. And these are smaller; they're 2 to 5 meters wide and maybe sort of tens of meters high. On a smaller scale, we get karst conduits or pipes. These are subspherical, elongate, sometimes vertical. So sometimes but often they're horizontal into the rock. They're usually quite small. This is an example with blue John fluorite lining the edges with calcite and some barite. And you can see these are sort of a meter scale appearing to the wall. But at the most extreme, we can get these pipes and tubes. So John is sat in one of these. And you see it's several meters high in this case, really, really spectacular. Calcite, galena, barite in this case. And then finally, we have these calcite cemented caves, and these are very irregular in shape. They're not always vertical, but they're definitely not strata bound. They cut across bedding. This is one example down on the south where we have this very irregular cave system. And on the margins, we see dissolution and corrosion. And it's completely filled by these very coarsely crystalline calcite crystals. I'll show you in a minute. But they're several centimeters at least in size. They're absolutely massive. Sometimes associated with these caves, particularly in the south, we get these funny little elephant eye features here, which are lined by calcite. So there's a set of associated small pipe type features with them. But they're striking because of the crystallinity of the calcite. It's so big, and there's virtually no other minerals present in these. These are some other examples. This is some rhombic calcite that we see in one of these caves in the quarry, several centimeters across. This is from treasury chamber. I showed you the Petrographical ladder at the beginning. These line the walls of that cavity, so we have much more elongate crystals again, pretty much the length of the hammer. And another example on the western margin where we see blocks incorporated within there with these elongate crystals. But most of them are these blocky calcite cements, really quite well formed rhombic crystals. They always seem to occur primarily in these non-strata bound hypogene caverns. And we thought at one point that they might, well, maybe they do still, would represent the last cementation event on the platform. And that if we looked at their geochemistry, we might understand a little bit more about the way the caves formed and when. We took lots of samples and we made some thin sections, and they were desperately disappointing. I was hoping to see lots of nice crystal zonation under cathodoluminescence, and we have transmitted light images at the bottom, cathodoluminescence at the top. I would have expected or hoped that we'd see systematic concentric zonation or cross-cutting relationships or something, and they really don't show very much at all. There's perhaps a little brighter rim around the edge of these crystals. They're mostly dull orange luminescent, very, very homogenous. Example here, but we saw nothing that really varied from this too much at all. So our first thought was, well, okay, you know, we can't break these down petrographically too much, but it does make the geochemistry a bit easier because, you know, we've sampled across these crystals, but we're not having to worry too much about lots and lots of different zonations and cross-cutting patterns. We sampled them isotopically, and there's a lot of data in here to break down, but all of the squares or the diamond shapes here are bulk rock analyses. Now they vary themselves quite a lot because of the amount of heterogeneity in the limestone as a whole. There's lots of precursor cements that are influencing these signatures, but for the most part, the bulk rocks have alteratino values of less than -9, and they have quite a wide range on their carbon. We sampled a lot of calcite from fractures to compare what we were seeing in these coarsely crystalline calcite cement in the caves. All of those really coarse crystals are these red ones here. We also sampled some calcite from these mineralised pipes where they're intergrown with ferrite and fluorite and galena. And a few, these are quite rare breccias, calcite cemented breccias. And regardless of where they were hosted, there didn't seem to be a huge amount of differentiation between the coarsely crystalline calcite, the vein calcite, the pipe, and the breccias. So whether they were filling caverns that were calcite only or whether they were filling mineralised voids, in terms of their oxygen and carbon, there's really not a lot of differentiation. The only thing that stood out was we have these coarsely crystalline calcites from Temple and Devonshire Cavern, which are near Matlock in the southern part of the platform, that have these very, very light carbon values down here. And what's striking is that this is an area where there was a lot of volcanic activity during the Carboniferous. So possibly there was some input of magmatic CO2 that's influencing this value down here. We then split them up. So we just lumped them all together, all of the different calcites, and said, right, okay, they're not showing any difference. So we'll just look at them by platform location and see if we get any differences. And then we do start to see a few things come out. And we see that in the north, around Castleton, we get these very, very light oxygens, but not much variation in the carbon. In the west, more towards the sort of the Cheshire border, we see much heavier oxygens and a bit of a range on the carbon. And then everything in the south and the platform tend to seem to sort of lump together, and it'd be hard to differentiate them in terms of their isotopic composition. And again, these samples in the south sit down here with these very light carbon values. So, you know, tells us some interesting things perhaps, but it's very difficult to unravel. We then went and used some, with some colleagues at Penn State, measured temperatures using clumped isotopes. And we found that when we plotted we used the temperature that we measured from the clumped isotopes, which ranged mostly from around 60 to about 102 degrees centigrade. A mixture of vein, crystalline calcite and pipe vein calcite, all of them showing a similar range, and used that temperature to calculate the isotopic composition of the water that precipitated the calcite. We see that one of the coolest samples has a fluid composition that's very similar to meteoric water. So meteoric water should have a delta 18O value of less than -0, -1 roughly. Anything above 0, anything positive, is more likely to represent a fluid that's been in contact with other rocks. So it's more crustal equilibrated, whether that be with mud rocks in the basin or with limestone on the platform. So we see this, not much of a trend, but we see the slight increase towards in delta 18O with temperature, very, very subtle, and the R squared doesn't really give you much confidence in that trend. And there doesn't seem to be much variation by platform position. So the comparison today, the thermal water that's coming out of the springs in Buxton and in Matlock and in a few other areas is somewhere between +4 and +16. I can't remember how that varies between different sites, but it very much sits at this higher end, suggesting that modern thermal water has undergone a lot of reaction, fluid rock reaction with the crust. Whereas the non-thermal water today, the groundwater is much, much lighter, typical meteoric water, less than -12 per mil, so way off the scale here of anything that we've calculated. What's also interesting, I don't normally do this, but I plotted the carbon values against temperature, and actually we get a much stronger relationship here, even though there's only a few samples. And we see that the lightest carbon, which again, negative numbers suggest groundwater, meteoric water. Cooler temperatures have the lightest values, and as the water temperature has increased, and so has the delta 13C, it's become closer to a marine carbonate value. And again, these are the modern values today, but both the thermal and the non-thermal water have quite negative numbers. But this would suggest that perhaps again with there was maybe groundwater coming in originally, but it was becoming more and more equilibrated with the limestone and maybe with some of the shales within the basin, and that was, but particularly with the carbonates buffering these values back to limestone values. We then ran ICP MS on all of these samples to see, potentially what the redox conditions were like, and ICP OES. The major ions are not particularly exciting. Modern day carboniferous groundwater has around 10 to 100 ppm manganese and iron. These calcite cements, the CL there, whether they're in the veins, the caves or the pipes, have much higher manganese and iron concentrations. So, well over 1,000 ppm of both in most cases. And that's suggesting that redox conditions were, it was suboxic to reducing, and the cathode luminescence would support that. So it's suggesting these coarsely crystalline calcites were precipitated in the deep subsurface away from much oxygen. In terms of other elements, we've got modern thermal water here in blue and average carboniferous groundwater in green. Sulfur, sodium, magnesium, strontium, for the most part, except for modern day groundwater, have much higher concentrations of all of these elements. And I've put the mean basinal shale values on here. So these are the carboniferous shales in the basins next to the platform. These have very high concentrations of sulfur, sodium, magnesium, and strontium. So it's possible that all of these elements came from either water migrating through the sandstones and shales within the basins, circulating very, very deeply, and possibly also picking up sulfur from basal evaporites. Simon Bottrell's done some good work in the past looking at sulfur isotopes, suggesting that there's been dissolution of some much older evaporites at the base of these platforms. Again, all of this is suggesting that the calcite cements were precipitated from deeply circulating groundwater. Rare earth elements can also help us with these interpretations. the total concentration of rare earth elements is very consistent with marine carbonate. If there'd been a lot of contamination by shale, there'd be much higher concentrations of rare earths and a much flatter profile than we see in each of these. Northern platform margin samples here have a very distinct marine carbonate signature. And that's not to suggest the calcite was precipitated from seawater, but rather that the calcite, the fluid the calcite precipitated from had dissolved a lot of limestone before it precipitated out, and that it's inherited that signature from the limestones it dissolved. Whereas in the platform centre and the west and the southern platform margin, there's a little bit more of it's very subtle, but there's a bit more of a bulge in the middle here. The southern data is a little bit more confused and maybe needs unpicking a bit more. And also that occasionally we see these little peaks in europium, and that itself can be an indicator of hydrothermal fluid. So we'll look at that a little bit more in a moment. But overall, this depletion in light rare earths and enrichment in middle rare earths and with greater or lesser extent heavy rare earths would suggest that the calcite was precipitated from pore waters that had been, again, undergone a lot of fluid rock interaction, dissolved a lot of limestone, maybe been in contact with some of the shales perhaps, and that possibly there's some low temperature hydrothermal fluids been input into the system as well. And I won't go too deep into this, but I think, that rare earth elements are complicated to interpret because you can get interference from different elements that make an anomaly look like an anomaly when it's not. So you have to normalize your data and then look at run a series of analyses to look at whether there's interference present or not. This plot of PR versus CE suggests that there is a positive lanthanum and negative cerium anomaly, which is very typical of marine limestone, probably inherited from the dissolved limestone. But also this range of cerium anomaly between 0.6 and 0.9 has been used as a proxy for suboxic conditions by other authors. So this would support our interpretation from our other data that precipitation of this calcite took place away from much, it was not an oxygenated environment, it was suboxic to anoxic. The europium anomaly that we see, saw in the previous slide, sorry, go back, these little europium peaks here, that can occur because there's interference from the middle rare earths, and by plotting GD versus EU, that helps us to pull out whether that interference is taking place. And it certainly seems that a lot of those europium anomalies are not real; they're an artifact of metal rare earth and interaction. But here, where we have a GD and an EU anomaly of greater than 1, this is suggestive of some form of positive europium anomaly, which would indicate an influx of hydrothermal fluids. So hotter, perhaps even deeper crustal fluids than just water that's interacted with the limestone. It may have interacted perhaps with the basement. And then finally, Trim-Hoffman ratio can also give us some indication of whether there's been interaction with the shales. If there's been a lot of shale interaction, we'd expect a YHO of around 28 or so, whereas a marine carbonate or seawater signature would be greater than 40. And any hydrothermal fluids we see would be significantly greater than 40 for that ratio. Most of our data is falling at sort of the low end of the marine carbonate range, suggesting definitely water rock reaction with the limestones, but potentially some limited interaction with the clastic sediment as well. And that's just plotted here. Sorry, I think to put two. Oh, I've just expanded the plot here to show that in more detail. I guess the holy grail with a lot of this, particularly when, in previous studies in the mineralisation, is trying to work out what age the mineralisation is. Because if we know that, we know when the caves formed, and there's been this long-standing debate about the timing of mineralisation. So we thought we'd have a try at getting some UPB dates on some of these calcites. Most of them don't have enough uranium or lead in them to get anything even vaguely useful. 3 samples that we managed to get a date on. You can see, for those of you who are used to looking at this data, that the error bars are big. We run this on the laser ablation ICP-MS here in Manchester, but we'll take these sort of 30-40 million year errors. Calcite cements, crystalline calcite cements, are coming out with ages that are upper Carboniferous to Permian. This is when we think the mineralisation was taking place from the pre-existing conceptual models, and it appears that the calcite cements that are precipitating away from that mineralisation also have a similar age, from fluids that are around 60 to 90 degrees centigrade in these cases, as determined from pumped isotope data. So what we're thinking at the moment, our hypothesis at the moment, is that coarsely crystalline calcite that's filling these hypogene voids and is also associated with mineralised pipes and breccias. So some of the calcite we've dated is from calcite only voids, but the signatures are very difficult to differentiate from the mineralised deposits. So we suggest that they're all roughly the same age and that they were all forming from upward rising fluids during this Variscan inversion event between the Carboniferous and the Permian. So there's already models of mineralisation of fault-controlled basin expulsion of fluids onto the Derbyshire Platform, and this seems to be consistent with solution of the limestone through these upward rising fluids and then precipitation of calcite and mineralisation within some of those voids. We then have this long period of pretty much nothing as far as we can tell. The Derbyshire Platform remained as a positive feature. There was a bit of deposition in the Triassic, maybe a little tiny bit in the Jurassic, and then it would have been covered by the chalk seas in the Cretaceous. And then uplift again during the Alpine orogeny. And we're proposing, of course we can't date it because there's nothing in them, that these open hypogene voids were formed much later, maybe from the Neogene onwards, associated, or Paleogene to Neogene onwards, associated with that second phase of inversion associated with the Alpine orogeny. So we're working on the fluid flow models. I don't have any models to show you at the moment, but these are our starting point. We're suggesting that the mineralised hypogene caves, those with calcite and those with calcite fluorite, galena and barite, were formed by these basin expulsion events that took place during the Variscan orogeny. And this is prior work that was, the reference has dropped off. Oh no, here we go. Prior work by Miles Fraser, who was a PhD student working with Fiona Whitaker and I. And he showed that the overpressure built up in the basins next to in the Edale Gulf, the Widmerpool Gulf, that built up during the Carboniferous through sediment loading, led to massive basin dewatering along faults during the Variscan inversion, and that fault control flux onto the platform resulted in not just in mineralisation on the faults, but dissolution of the limestone and mineralisation of the hypogene voids that were formed. The modern system, this is a broad cross section of the sketch that was presented by John Gunn in 2006. The modern hydrogeology that John has sampled waters across the platform suggests that there's topographic flow from the high area to the west of the carbonate of the Derbyshire Platform, and through this plastic basin and up to give us the Buxton thermal spring, and then also down this convection through the Bakewell fault zone up to the Matlock spring. So this is sort of a working hypothesis that we're going to develop for the modern day open hypogene voids, that was some form of deeply circulating topographic flow that helped form not just the hot springs, but also these big open hypogene cave systems. But to go back to our hypotheses, first one was that all the non-strata bound caverns formed from the same time from the same fluids. We don't think that. we think that they probably formed at different times, either pre-mineralisation in the Variscan orogeny or much more recently, and those caves remain open. But in both cases, there was probably a strong component of groundwater. The geochemical data is suggesting deeply convected groundwater that's interacting with the limestones and potentially with the shales within the basin. All the non-stratabound cavern types are hypogenic. They've formed from uprising fluids. Yes, I think that is true. We don't see any really strong evidence of non-stratabound caves that are not hypogenic. But there is complexity in the system because the modern epigene caves that form from glacial outwash have used some of these cave systems and enhanced them a little bit. And then the coarsely crystalline calcite cement are associated with the dissolution temporally and spatially. We think that's the case. We think that they're the strongly rock buffered signature that we're getting of these cements, indicative of extensive dissolution of the limestone. In terms of why the caves form, this is work that's still going on at Bristol with modelling, but calling of upward rising brine, yes, I think that's probably very important. The igneous intrusions we think are a bit of a red herring. We think most of the volcanic activity took place before these caves formed, and that any low pH fluids that were released at that time maybe buffered very quickly and didn't form very big caves. But there is some indication from the carbon isotopes that there was perhaps a little bit of calcite cementation associated with CO2 injection. And then fluid mixing, quite possibly. There's good evidence of high concentrations of lead and of fluorine and barium in the basins that probably supplied the cations for mineralisation. And so dewatering of the basins mixing with these groundwaters was probably very important, and maybe that contributed to the dissolution. And so to finish, the hypogene caves that we found occur in a range of sizes. They have a complex morphology, and they're mostly associated with faults and fractures, maybe not directly, but they're definitely forming in close proximity to some of the major faults. The calcite in the caves where there's only calcite very much resembles the calcite in mineralized fractures and pipes. The precipitation of that calcite seems to be sort of 60 to 102 degrees centigrade, suggesting meteoric through to quite evolved crustal fluids precipitating it. The trace element data suggests lots of fluid rock interaction with the limestones. I should say limestones as well as shales there. There's just good evidence of deep circulation and fluid rock interaction. Probably at least some contribution from meteoric water in the system. And we think that maybe the modern open caves are much younger and associated with the alpine orogeny, but really quite difficult to date because there's nothing in there to sort of hang our hat on. And I should finish with that. I just want to say thank you to all the caves and the British Cave Research Association who've just provided us a huge amount of support in terms of access and safety and everything else. And Jim Riding at the BGS and Alexander Klimchuk, who unfortunately died a couple of years ago, but was here briefly in Manchester. And he was the world leading expert in hypogene caves. He published more than anybody else on these, and he was extremely excited by what we showed him when he was visiting, and gave us a lot of advice in terms of the terminology and so on. And you know, I think that there's a lot more to be done here to try and link this into what we see in other parts of the world. Thank you very much. And I'm happy to take any questions.
Thank you very much, Cathy. It was fascinating. I think because we're a fairly small group, you're welcome to use the chat, but you can also just stick your hand up and ask a question straight out. Pretend we're sitting in the same room.
I think Charlotte had a hand up.
She's
waving. She's waving.
And, applause, virtual applause.
Thank you.
But virtual questions are no good. We need real questions, so I'll give everyone a moment. Thanks, Charlotte. Charlotte, ask a question, please do.
Sorry, my mouse is doing strange things. Thank you, Cathy. That was great. In terms of thinking about, you've obviously got really good analogies from near surface. And in terms of thinking about those depths that you might want to use as targets for geothermal, so maybe 2 kilometers depths or so, what do you think would be the differences that you might find? Would you find more? I know you didn't kind of go into the sediment filled ones as much, but would you expect to find more of that? Would you find more mineralisation? Would the voids be different, do you think? How do you think that would impact?
So I think the question is how much collapse of these open voids? Well, would the open voids be there if they'd never been brought? If that limestone has never been brought close to the surface, those open voids may not be there. If they had formed, I mean, if we're wrong about the timing, or if they had formed for some other reason, the question is how big would they be, or would they have collapsed? And if they collapse, they could still give you quite significant flow perturbations, because you'd have brecciation and so on. It's interesting. One of our advisory board members is from Vito in Belgium, and they have mapped some discontinuities in seismic, which they interpret to be hypogene quite independently. And that's at depths of 2 or 3 kilometers. Now, from what they show me, it's really hard to tell, and this is never, the seismic data through Carboniferous is never great. But there is some suggestion from that data in Belgium that perhaps there are some form of void systems there that are not pure epigene karst tied to unconformities or emergent surfaces. So I think the big problem with the Carboniferous is how much flow are you going to get out of it anyway. And the fractures are going to be critically important. But is this going to give you some extra permeability around fault zones, perhaps? Possibly.
Thank you.
Okay. Yeah, Bob.
Yeah, so I may have missed it because I had to step out for a couple of minutes, but is there any evidence that of the relative timing between your void formation and faulting?
Good question. So not really. I mean, I think we've got these sort of closed couple of tubes that are cutting through the dirt low rake, which I don't know if you were there, that was quite early in the presentation. That, oh, my seized up now. There we go. I'll just stick my thing back on again. These, come up. There we go. These chimneys here.
That I did miss this, yeah.
Yeah. So a big strike slip fault, you may even have been into this fault, really lots and lots of strike slip movement in here. Calcite cemented cavities, and then these are cutting through. So of course this is all mined out, which makes it, but the mining has taken place along that side there. So the trouble with these fault systems is they've been reactivated so many times. And nobody's really got to grips with the history, the kinematic history, and the structure. So you definitely get these features along fault zones. And if those faults were moving, those faults would obviously have been moving during the Variscan orogeny for sure. The question is how much further movement was there after that. There was obviously the extension in the Mesozoic, and then there was a little bit of movement during the Alpine orogeny. So yeah, I think there's still work to be done on really tying it in properly with a good structural analysis, and really getting a field-based paragenesis in place as well.
Yeah, it's just that if the faults are forming in a relatively near surface setting, so by which I mean 2 kilometers, they actually, particularly in rocks like limestones, they can actually be very effective agents of void creation, should we say?
Yes.
And
and I guess there's certainly, well, these are really wide faults with lots and lots of mineralization along them. It's just that's all been mined out now. So there definitely was a lot of a lot of fluid flow and presumably a lot of dissolution associated with that when those minerals precipitated. And maybe that keeps going. And I don't think, I mean, this is shallow. It's never been down more than a couple of kilometres, really. It's just sat there.
Yeah.
Burial history is really tricky because there's no evidence of anything really being left on top, and some of it, particularly on the west side, may not even have been properly buried in the Carboniferous, we're thinking now as well.
Yeah. Okay. Thanks.
Yeah. Okay. Yeah, sure.
Hi, Cathy.
Hey.
Lovely to see an academics in their office working in the
I
university.
know. I came in specially.
Brilliant. I'm just going to say, I saw you were suggesting some of the fluids perhaps were coming from dewatering and some of the mud rocks. Do you see any direct evidence of silica mixed in with any of the carbonate cements you've had?
Yeah, so the silica is another bugbear, really. There's definitely hydrothermal silica, by which I mean, sort of euhedral quartz and silica cemented faults in parts of the platform. Not in that one I've just shown you there, but down towards Matlock, there's not a lot. And also, actually, and Trevor Ford recorded it as well. Actually, no, he did. Yeah, not that part I've just shown you. Actually, yeah, Trevor recorded some silica down at the other end of it. And a lot of that again has been quarried out now, but it's definitely, there's track records. So
do you then think that, Cathy, then that is all coming, all that silica that potentially there, all the dewatering fluids, is coming from the mud rocks, or is it also coming from the sands and infiltration of later phase fluids coming through?
Yeah, or some of it could have even been volcanic in places. The timings on the igneous intrusions, we know that there was extrusive volcanism during deposition, probably can rule that out, but there's also intrusive volcanism, which nobody's really dated particularly well, but it's somewhere in the Numerian Westphalian.
Okay.
But yeah, in the basins, there's super high concentrations of fluorine and zinc, which are fluorine and lead, which I definitely think is the source of the mineralisation. The barium might be from the sands. There's less in the mud rocks, but more in the sands.
Okay.
Which could tie in with the meteoric fluid coming through as well.
Okay.
Yeah.
And so then partially linked to that then, do you think then these hypogene sort of cavities have potential for CCS?
Well, that's a good question. Yeah. It really depends on what how they preserve in the subsurface and how open they remain. I think there's interesting questions around this coarsely crystalline calcite as well. I mean, we were originally wondering if there was a natural CO2 injection, whether they were a reflection of that. And I think in places they might be. It's just really hard to pinpoint. But where we get those really light carbon signatures, like minus 12 or whatever, in an area that was volcanic, it makes me think that it sequestered some of that natural CO2.
Okay, so do you think some of those later sequestered carbonates then are more resistant to further acidic pore fluids perhaps going through? So
possibly. I mean, they're very coarse, so they're not going to be particularly reactive. I think the thing that fascinates me is they must have been so slow growing to form so well, but the fluid composition didn't seem to change that much.
Right. Okay.
So yeah, they're quite intriguing. But yeah, whether I'd be nervous of suggesting anything big like that could be a good storage, something good for storing something like CO2, because A, they're associated with faults and fractures, and B, stuff gets out. To form them, the fluid must have got out somewhere. So
I was just more wondering from the case of being perhaps counterintuitive in thinking that, you don't necessarily want to store CO2 in a carbonate, but if there's something we can learn about how it actually precipitates into carbonate itself, and how we can then put that into clastic reservoirs, which are, maybe some of the trial projects going on around the country.
Yeah, absolutely. No, I think there's a bit more thinking to be done there, because there are some studies that suggest that if you inject in certain types of carbonate, you can in situ mineralize quite quickly, but it's very texture dependent, aren't they? Yeah. So yes.
Okay. No, lovely. Okay. Thank you, Cathy. Thank you.
Okay.
Well, I'd like to say thank you, Cathy, for a really interesting seminar and good questions. And
yes, thank you.
Thank you for joining us. Look forward to seeing everyone at the next DI seminar. You've all had emails, no doubt, telling you